I can get more values. Now I would like to substitute these values of C1, C2, C3, C1, C0 and C1 are our constant, which we don't need to repeat because the solution is in terms of C0 and C1. The other values we rewrite, and value of C2, C3, C4, and I can write my result is the following. I get here the value of y is equal to y with the value C0 plus C1 x plus C2. What's my C2? My C2 is minus lambda square or 2 factorial C0 minus lambda square or 2 factorial C0 x to the power 2. C3 is minus lambda square over 3 factorial C1 minus lambda square over 3 factorial C1 x to the power 3. Then is C4. What's my C4? My C4 is equal to lambda 4 or 4 factorial C0 plus sign plus lambda 4 or 4 factorial C0 x to the power 4. Now C5. C5 is lambda to the power 4 5 factorial C1 lambda to the power 4 5 factorial C1 x to the power 5. Then we're having minus C6 and C7 and so on, then plus and so on. Now I combine the terms with C1 and C0 and C1 together. When taking together, I get here C0 out, I get here 1, I get here minus lambda square x square over 2 factorial, then here plus lambda 4 x4 or 4 factorial, then we have minus, and then here plus and so on, plus C1, and we are having here the value, this here C1, we take out, we get x, then we are having here minus lambda square x to the power 3 or 3 factorial, and then we are having here plus lambda to the power 4 or 5 factorial x to the power 5 and minus and plus so on. So this is my solution. This is my y1. My y1 is equal to 1 minus lambda square x square or 2 factorial plus lambda 4 x4 or 4 factorial, and here is minus and plus so on. My y2 is equal to x, then we're having minus lambda square x cube by 3 factorial, then plus lambda 4 x5 by 5 factorial minus plus 1. So this is my series solution for the given differential equation in terms of two functions. We are having here C0 and y1, and here is our general solution. We are having two arbitrary constants, C0 and C1, and here just written a y is equal to C0 y1 plus C1 y2. I just give you some more information, some hints about this one. Before doing that, I just want to revise it. I was given here this differential equation. We check the arbitrary constant. We find here a2 of x is equal to 1 and x equal to 0 is ordinary point. So we said we can write the solution about x equal to 0 in terms of series. We get here y, we get y dash, we get y double dash, substitute there. And then we just have the series form of this. Here in this equation, we say this equal to, say it is 1. This equation, when we substitute y equal to sigma n is equal to 0 to infinity cn x squared and y double dash. Now we compare the coefficient. We want to make it x, m, and matrix m. We pay m minus 2 is equal to m and n is equal to m. Then we change all the values of m, n to m. So this here is when n is equal to 2, then here m is equal to 0. When n goes to infinity, m goes to infinity. Mn, when n equal to 0, m is equal to 0, n goes to infinity, m goes to infinity. We change our n's to m by using this transformation, and we get here this equation. Now luckily, we're having here, again, m is from 0 to infinity, m is from 0 to infinity. We don't need to make any change in summation. We take it out and x power 1 out, then compare the coefficient, 0 x to power m. Sigma m is from 0 to infinity. all the coefficients are equal to 0. M is from 0, 1, 2, 3. So this is my recursion relation. From this recursion relation, I can get the values of C2, C3, C4, C5 in terms of C0 and C1. Why? Because second order differential equation, we can get two arbitrary constants, C0 and C1. Here I started here, I take C equal to 0, then I take C equal to M equal to 0, M equal to 1, M equal to 2, here we get M equal to 3, we get here M equal to 4, we get M equal to 5, and so on. And then we write our equation and simplify this one. This becomes lambda square by 2 factorial minus sign C0 minus lambda square 3 factorial C1, then positive sign, then 2 negative sign. I substitute the values here in my equation, in my series solution, the values of C2, C3, C4, substituting here. Then we group together the values with C0 and the values with C1, and we get here this equation y equal to y1 and this y2, and right here y equal to C1, y1, and C0, y1, and C1, y2. Now, as I said, I just make a small extension and give you more idea about that one. Here we can see that we are having here the series, and I can write this series as sine and cosine series. You can see our first series y1 is a cosine series. We can write this is equal to, or y1 is equal to, what's my y1? My y1 is equal to 1 minus lambda square, lambda into x whole square, or 2 factorial plus lambda into x 4 over 4 factorial, then minus plus 1. This is my y1, and this is equal to cosine lambda x. Then here y2, we're having here lambda square x, we have lambda 4x. So I take here 1 over lambda, I divide by lambda, and I multiply by lambda, I get here lambda x. This, we have minus lambda cube x cube, or 3 factorial, we are having my plus lambda 5 x5 or 5 factorial, then minus plus 1. Because multiply by lambda, this becomes lambda, this becomes lambda cube, lambda 5. So this is my y2 is 1 upon lambda into sine, we have sine lambda x. So I can write my solution, my y is equal to C0 cosine lambda x plus C1 over lambda, we have sine lambda x. So here I can write here C over lambda is a constant, lambda is also a constant. I can here y equal to C0 cosine lambda x plus here we get here C2 sine lambda x. So we can have the solution in terms of the function sine and cosine. Moreover, if we see this problem, this is also not the problem which we are going to apply the series solution for that one, only just to show that we can apply the series solution and get the same is validity of the understanding of the series solution. I am having here the differential equation y double dash plus lambda square y equal to 0. We can here use y is equal to c e to power mx. I get recursion relation m square plus lambda square characteristic equation m is equal to plus minus lambda I. My solution will be y equal to alpha is 0, beta is lambda, so cosine lambda x plus c2 sine lambda x. That's the simple solution for that one. But we have found the solution with the series also. I give you some more examples. Here, these are the two examples where I said we can solve it by other method also. But they are the examples. We can't solve by any other method. We are bounded to solve it by the power series. That will be my next example.